Okay, welcome to lecture here. We're continuing on in chapter 2. And should not hit so many things. There we go. Try that. Do that move. We'll move a couple things around here so I can actually see the screen. That would be helpful, I'm assuming. Make sure you type here in the chat there for roll. And here we go. All right, so we are talking about chapter 2. So we've really been talking about sort of energy waves, um, and how to calculate all that, along with electrons as they transition from one energy level to the next. And a couple of just reminders, some of the one stuff we talked about. Again, we saw that c is equal to the wavelength times the frequency, c being the speed of light, which is that constant of 3 times 10 to the 8 meters per second. We have our frequency here, which is usually in reciprocal seconds. Again, a reciprocal second is the same as a hertz. So that's, again, another very common unit of frequency that comes about. And in this formula here, the wavelength is in meters. And again, it's in meters so that it will cancel out correctly with the units over here with our speed of light. So obviously, as we saw this one, we could use it to calculate the wavelength or the frequency, which is essentially the same calculation. Um, you're basically going to take the speed of light over either the wavelength or the frequency to calculate it. We also saw an energy equation equals h times the frequency, h being our Planck's constant, which is that 6.63 times 10 to the minus 34 joule seconds. And again, the frequency obviously being our reciprocal seconds. And again, in that case, both of the seconds will cancel out, leaving us just joules, which again is a unit of energy, which is what we're looking for. We also saw that we could tie both of these sort of equations together, and you get E equals h times the frequency. And since, as we see up here, the frequency is the speed of light over the wavelength, you can pop those guys in like so, and that gives you hc divided by the wavelength. And the nice thing about this is, again, h and c are both constants, so you always have that number. And obviously, if you just have the wavelength, you can figure out, obviously, the energy associated with that. We sort of finished up talking about the idea of electrons really sort of transitioning from one energy level to the next. And that's what really the n number is here. This is, again, what is referred to as the principal quantum number, which is a fancy way of saying energy levels. So n equals 1 is the lowest in energy, or the ground state. So that's the one that is closest to the nucleus. As you go above that, n equals 2, 3, 4, all the way up to 7, we're getting higher in energy. So those are, again, sometimes referred to as excited states, and further away from the nucleus as we go up. So we did see an equation where you can calculate the energy change that occurs as an electron really goes from one energy level to the next. And that was this guy here. The change in energy is minus 2.18 times 10 to the minus 18 joules. That, again, is what is sometimes referred to as Rydberg's constant, or RH. And that is 1 over our final energy level minus 1 over our initial energy level squared on both of those. And again, we could use that to figure out how much energy is changing in terms of the atom as it goes up or down in terms of those electrons as they transition. And this E here, essentially the same deal here. So you could set this whole thing equal to everybody that is here. So again, you could use it to use the H in the frequency. You could use it over here with this as well. So again, all those guys sort of run together, and you could use all that. Remember, in terms of energy, when we do calculate energy, we do want to make sure that we keep the negative if it is negative, or obviously leave it positive if it is positive when we do calculate it. And again, a negative value for energy means that overall it's an exothermic process. And exothermic process means that heat and energy is being released. And if we calculate energy and it is positive value, it means it's an endothermic process. and heat and energy is being absorbed. So when we talk about electrons transitioning, say from n equals 1 to say n equals 2, in this particular case, if the electrons started at the bottom at the n equals 1, it would be endothermic in terms of the atom. It would gain energy, and that would allow the electron to go up to the next energy level. While if we had an electron in an atom that was starting already up at the second energy level and wanted to go the opposite way and back down, it would be exothermic in terms of the atom, as it would have to give off that energy when it does, the electron transitions down. Again, that's the idea of the law of conservation of energy. We don't lose energy or create energy, so it is transferred from one place to the next. So if somebody loses a certain amount of energy, somebody else will gain the same amount of energy. And the way that we signify whether exothermic or endothermic is really important when you calculate something with energy is through that sign of it, either negative or positive. Again, it allows you to understand if what you're dealing with is overall an exothermic reaction or an endothermic reaction. Now, with that being said, like we talked about last time, there is obviously, as we did an example here and you did some calculations in that lab, that you do have to sometimes continue on and use that energy value and say a formula such as what we got going on here, that the E equals hc over the wavelength, or even this one here. And when we do then take that energy value and use it to calculate something like wavelength or frequency, we do want to turn it into a positive number if it is not. And again, the purpose of that really is just a logical purpose. We cannot have a negative wavelength or a negative frequency. So those things do have to be positive values. So that's what we were talking about last time, that if you're going to continue on with the calculation and use that energy value in another calculation for wavelength or frequency, if it happens to be negative, you do need to make it positive when you do that, so you don't end up with any type of negative wavelength or frequency. But again, it's important to keep the negative on the energy value because again, it's important to signify exothermic or endothermic. Any questions on that stuff we were talking about here? And in addition, yeah, you do need to know formulas. They will not be provided for you. So you do need to know formulas on exams and quizzes. Any type of constants or conversions will be provided for you. So for example, like the H number there would be provided for you, Planck's constant, speed of light would be provided for you. Even Rydberg constant, I think, will be provided for you as well. But you do need to know kind of the formulas like, C is equal to wavelength times the frequency, the E equals H times the frequency, those type of things you do need to know.
Wait, Professor, I have a question.
Yeah.
So hertz and reciprocal seconds, there's no conversion factor for that, is there?
Technically, it's a one-to-one, so really there is no real conversion. It technically is a one-to-one relationship, so they're the same thing.
Okay.
It's kind of like you just need to change the units. It's very similar to like what you do with like milliliters and cubic centimeters. It's a one-to-one relationship basically. So
okay, I get it.
The number doesn't change, you just change the units. You're welcome. Any other questions on that?
For the units for frequency, so we can put either seconds, reciprocal seconds as a units, or hertz, and that'll be correct.
Yeah, technically they're the same thing. And although most people will do reciprocal seconds, but technically speaking, because it is a one-to-one relationship, it is almost the same thing as you could write hertz or reciprocal seconds. Okay. Now, sometimes you will get like a prefix with hertz. So for example, like on the, I think we had an example earlier where we were talking about sort of radio waves. And that's basically when you turn your dial to like, 95.5, it's really 95.5 megahertz, right? So sometimes you'll see a prefix on hertz, like megahertz or something like that. And again, that is different than just reciprocal seconds. Again, you have that mega prefix that you have to take into account. Other questions on that? Okay, so as we were talking about, really, as these electrons are transitioning downward in terms of energy, they do have to release that energy in the form of a wave of light. And depending on where the wavelength is for that particular photon that comes off, it may fall somewhere in that electromagnetic spectrum that we were talking about. And remember that there's really only one part of the spectrum where we would see color appear, and that's the visible part of the spectrum. So again, if that wave is coming off in that visible part of the spectrum, you know, we will see those colors like red, blue, whatever it may be. But it doesn't necessarily have to be in the visible part of the spectrum that comes off. So for example, you can have a photon of light that comes off, for example, in the infrared spectrum. You wouldn't see light, could be microwave or maybe even UV or X-rays or something like that. And obviously you wouldn't see any type of color associated with it, again, because it's outside that visible part of the spectrum. So I think on the lab, there was one of those that you calculated was actually outside of the visible part of the spectrum. And again, you wouldn't see a color associated with that particular one because of that. Any questions on any of that stuff there? Okay, so I think we did this one in lab. We went through the calculations again. Very similar to what you did on the actual experiment as well. So then let's continue on with sort of this idea of electrons, maybe if it lets me go, there we go. And sort of this idea of, we talked about sort of the dual nature of light. So this is the idea, again, Einstein sort of came up with sort of this idea a lot, that particles can have certain wave-like functions and waves can behave like particles. And sort of the idea behind this is, one of the ideas here was thought of as de Broglie, and he proposed that basically particles could have these wave-like characteristics. And he predicted that the wavelength of a particle is inversely proportional to its momentum. And particles, although they're very small, something like an electron, for example, the wave character that it has is really significant. And really where this is leading us to, if you remember, we sort of also talked about Bohr and his model of the atom, where electrons, again, are traveling these pretty kind of circles, this planetary model around the nucleus in these orbits. And as we talked about, it does explain those sort of lines that we see in hydrogen. But as we sort of move away from hydrogen, when we get more than one electron involved, it doesn't really hold up very well. And so we're sort of moving with de Broglie and a couple other things we're going to talk about here in just a second, away from that idea of this sort of planetary model to this idea as sort of where we're at with in terms of electrons, that electrons, which are particles, they are traveling in these sort of random pathway, and we really don't know exactly where they are at any given point in time. So this is the formula for de Broglie's wavelength, which is the wavelength is equal to h times the mass times the velocity in meters per second. Now, when we do some of these units here, there's a couple of things important when we do calculate the de Broglie wavelength in terms of units. And the first thing has to do with this guy right here. And by the way, there is a S missing here, a second. There should be another second right about there. So you might want to add it to yours. And when we look at this, this is actually what a joule is equal to. So a joule is a unit of energy. And I think we saw it at the end of the last chapter. It is the same as saying a kilogram times a meter squared divided by a second squared. And that is sort of the same thing as basically what a joule equals. So if we go into our de Broglie wavelength here, H, which if you remember, H has units of joules times seconds. And H is that 6.63 times 10 to the minus 34 joule seconds. So if we put those units in, joules times seconds, divided by the mass, and the mass has to be in kilograms, and we're going to times it by meters per second. And the reason why the mass here doesn't have to be in grams, but needs to be in kilograms is because of this relationship here. If we substitute in this guy for that, as you can see on the bottom there, we get kilograms, meters squared, second squared. And again, that is what a joule equals. And if we times that by our seconds, and divide it by kilograms and meters per second. 1 second here, 2 seconds here, cancels out both seconds there. Kilogram cancels out a kilogram. A meter cancels out 1 meter. And again, the only unit left at this point is a meter, which is good here. And what this really means is, honestly, this is still a constant. So you could still write it 6.63 times 10 to the minus 34 joules times seconds. Again, just remembering that joules equals this. The important part really is the bottom part here. You need to make sure that when you use the de Broglie wavelength, really the only thing that you sort of have to worry about is the mass needs to be in kilograms and the velocity needs to be in meters per second. And it's really just so that everything cancels out correctly. Again, if you're not, if you don't really have that, those guys in those units, things will not cancel out correctly and you will be off. So de Broglie actually didn't do any sort of experiment on this deal. He just sort of came up with this idea, and he sort of thought of it as like a guitar string, for example. When you pluck a guitar string, right, the wave is sort of a standing wave. So there's like an amplitude, right, and it's still moving and motion. And he actually was proven correct later on when other people did experiments. But this is, again, sometimes referred to as the de Broglie wavelength. And you do need to know that formula there. So why don't you take a second and calculate the de Broglie wavelength here for an electron that is traveling at 2.65 times 10 to the, it looks like 8 maybe, meters per second. Actually 6 meters per second. Let's see what you come up with. The mass of an electron is right there, 9.11 times 10 to the minus 31 kilograms. Okay, so again here, we're going to calculate that de Broglie wavelength, which is, the wavelength is hm times the velocity. Here our velocity is in meters per second, so that's the right unit, and they were nice enough to convert that into kilograms as well. So really, we just need to plug it in. So again, h is 6.63 times 10 to the minus 34. Again, it is joules times seconds, divided by our mass in kilograms, and our velocity, which is in meters per second. So that's all good. And again, a reminder that that joule is a kilogram meter squared second squared, which is the joule part of it. Just put the J above it. And again, we still have that seconds divided by everybody that's there. And again, that is how all the units sort of properly cancel out. times 10 to the 6 meters per second. Again, seconds will cancel, kilograms will cancel, one of the meters will cancel, and it will leave us 1 meter that's left over in terms of the units. And if we do all that, it looks like 2.74 times 10 to the minus 10. And again, the units here are meters. Any question on that calculation there? So really this de Broglie's sort of wavelength and his sort of idea and his thought, like a lot of experiments that were going on, that, you know, particles like electrons do possess sort of that dual nature, wave-like function and particle-like function. Again, we're going to move away now from sort of the Bohr model and kind of transition into what is sometimes referred to as a quantum mechanical model of an atom. And again, this idea is moving away from that planetary model of electrons and orbits to really this idea of sort of probability. And we really are not sure exactly how electrons are traveling around the atom. And that brings us to, there it is. That brings us to this idea that, you know, as we learn more about how a particle like an electron is moving, the less we know about sort of its actual position, and vice versa. The more we know about the particle's position, the less we know about how it is actually moving. And that is what is sometimes referred to as the Heisenberg uncertainty principle. And this is actually what this is here. Delta X is the uncertainty in the particle's position. And over here, delta MV is the uncertainty really in its motion, really, and how it's traveling, its momentum. And it's greater than or equal to H, which is Planck's constant, 4, and then that's our normal pi, 3.14. And because it's sort of greater than or equal to, there's this sort of idea that, you know, you can almost think about it as sort of an inverse relationship. As you learn more about something, you learn less about something else. Again, as you know more about how it's moving, less about its position, and so forth. So this is certain uncertainty in how a particle can move. And obviously an electron being a particle, this is moving us away from that Bohr's idea of knowing exactly where we should come across a particle like an electron. So because these particles are also thought to have sort of wave function, and the idea of like the guitar string where, you know, the wave is sort of, it's on both sides of the guitar, right? So the string can't really go anywhere, but you can see the wave move. You could kind of think of the nucleus, right, as a point where, you know, the particle is sort of tied to it and it's moving in sort of a wave-like fashion. And what we move away from this idea of knowing for sure exactly where an electron will be to this idea of the best we could do is think about it in terms of probability, or where there's a good probability of finding something like an electron at any given point in time. And this gets us to sometimes referred to as probability distribution. And we sometimes will see probability maps as to where we expect to find electrons. And sort of the biggest sort of probability maps, if you will, are things that you may be familiar with. We move away from this idea of orbits where electrons are housed to this idea of they are housed in what are known as atomic orbitals, right? And atomic orbitals, as you might remember from electron configuration, we'll talk about again, there's s orbitals, there's p orbitals, there's d orbitals, there's these sort of f orbitals. And really what these things are sort of probability maps of, in an electron, you know, this is where I think there's a high probability of finding an electron in an atom. And we'll talk about a little bit more later, but again, you may be familiar with a couple of things. And since we got some space here, any individual orbital, right, could hold 2 electrons maximum, right? And when we talk about s orbitals, there's only really one type, and that means you can max out at 2 electrons if you filled it up. P orbitals, as we will see, there's really 3 types of p orbitals: px, py, and pz, which means if you max them out, you can max out at 6 electrons. D orbitals, there's 5 different types of d orbitals, which again, if you max them out in terms of electrons, that would be 10 electrons, 2 each. And lastly, f orbitals, there are 7 different types. And if you max them out, you would be at 14 electrons maximum. So, although we think about this as electron configuration, these are orbitals, blah, blah, blah. What is really that? What it really is, again, is these are really just sort of probability maps based on calculations of where we would expect to find an electron in an atom. Now, if we find a place in the atom where we would expect a high probability of finding an electron, that does not necessarily mean that we know exactly how it got there or where it's traveling, how it's traveling. We just know that in this particular spot in the atom, there's probably a fairly good probability that at some point, not sure how it got there, but we would find an electron present. And if you just kind of think of this little density map here, the darker areas are higher probabilities of finding electrons. As you fan out, it gets lighter in color, and those are lower probabilities of finding an electron. And we sort of envision probably your nucleus is, somewhere in this area. So you can see the darkest area is right around where you would probably expect the nucleus to be. And as you sort of fan out away from the nucleus, it gets lighter and lighter in terms of their probability. And that does make sense based on what we'd also talked about, which is that idea of opposites attract, right? So our nucleus right there is positively charged. We have electrons which are negatively charged. So there is going to be some attraction, obviously, between the overall positive charge of the nucleus and the negative charge of those electrons, which are moving around. And here again is a probability distribution. And you can see as you start to fan out from approximately where our nucleus is thought to be, we do start to see the blue color kind of get lighter and lighter and lighter. So obviously out in perhaps this area, less of a probability of finding an electron than probably closer in near where we would expect the nucleus to be. Again, with Heisenberg's uncertainty principle, we don't know exactly how that electron is truly traveling at any given point in time, or exactly where it's located at any given point in time. So when we talk about orbital size, they're really what are known as wave functions, and we definitely don't get into wave functions in this class. If you continue on in your chemistry career, you probably will hit a class known as physical chemistry. I'm sorry, but you'll hit a class known as physical chemistry. It was a good 2 years of my life. It's okay. It was a one-year class, but it was a good 2 years. I thought went very well. But the whole first semester really of physical chemistry there, you talk a lot about wave function and calculating. They're kind of like derivatives and a lot of calculus sort of calculations. But we sort of think of them really again as these sort of wave functions, and really they're just probability sort of maps of sort of these theoretical areas within an atom as to where we would sort of find an electron. So the hydrogen 1s orbital, and the 1s, as you probably know, the 1s, the 1 there means that it's on the first energy level. The s here is the orbital which it is in. And again, an s orbital, as you also may be familiar with, is simply a sphere. And it gets larger as you go to every individual energy level. And again, with the highest probability, in that center area, again, lowering that probability of finding that electron as you sort of go out from the center where we would expect to find sort of the nucleus. So where we're kind of going with all this is into sort of electron configuration. And we're going to talk about, now really why there are these different orbitals, why there are S's, P's, D's, and F's. And you'll go back to thinking, wow, I wish I just only knew about writing electron configuration and not all the stuff of how we actually know there's like 3 orbitals and all this kind of stuff. So this is all sort of based on this idea of this wave function, these calculations. And this brings us to the idea of quantum numbers. And quantum numbers are, there's really 4 types of quantum numbers. And ultimately, they are how we get to those orbitals and how many orbitals are when we're doing things like electron configuration. So let's talk about the different types of atomic numbers, different types of quantum numbers. And the first one is the principal quantum number, and that is abbreviated with N. So we sort of have seen it already here, but the principal quantum number, which is N, is really, for the lack of a better description, it really is sort of the energy level. So as we talked about, N can have values of 1 through 7. And again, N is equal to 1 is that ground state, and that is the lowest in energy, while anything above that, N equals 2 to like 7, these are again what are referred to as excited states of energy. And again, they're usually higher in energy, and as you go from say 1 to 2 to 3 and so forth, you're sort of in theory moving further and further away from the nucleus in this particular case. So N can have values of 1 through 7. The next quantum number is what is known as the angular momentum quantum number, abbreviated with an L. And that really is sort of the shape of the atomic orbitals. These are really what are sometimes, this is really how we know we're talking about a S orbital, we're talking about a P orbital, we're talking about a D orbital, talking about an F orbital, or whatever it may be. And L can have values, I'll go this way with it. L can have a value of 0 to n minus 1. So that angular momentum quantum number, which is abbreviated as an L, it can have a value that ranges from 0 to n minus 1, all whole numbers as you do that. So for example, if n is equal to 1, L would equal 0. It's your only option in that particular case. The next one is what is known as the magnetic quantum number, which is m sub L. And m sub L is sort of the orientation of those orbitals in 3-dimensional space. So how we have 3 different p orbitals, for example, px, py, and pz. What the x, y, and z means, like in math, right? We have an orbital on a different sort of plane in 3-dimensional space. You know, we have an orbital hanging out over here, an orbital on this guy, and so forth, an orbital on the other guy. And that's really what the m sub L number represents, is the orientation in 3-dimensional space. Second to that is it will also tell you how many different orbitals there are for a particular subshell. And m sub L runs from negative L to 0 to positive L. Again, all whole numbers that go through here, and we'll do some examples in just a second so you can see it with sort of real numbers in just a sec. But it has a value that could run from a negative L value that you have to 0 to a positive L value. So we have the N value, which is the principal quantum number, essentially the energy level. We have the L value, which is the angular momentum quantum number, which is basically the shape or the type of orbital that's present, or subshell. And we have m sub L, which is basically the orientation of those orbitals in 3-dimensional space. The last of our 4 quantum numbers is the spin quantum number, and that is abbreviated as m sub S. And I moved the slide ahead, so you might actually have this slide a little further down in your notes. But the m sub S is the 4th quantum number, and it is the spin quantum number, and it has a value of +1/2 or -1/2. So basically what this represents is the idea of the orbital itself and the electrons when they go into an orbital. they have spins. And when electrons go into an orbital, represented with an arrow, we usually point it up, and that is what is referred to as having positive of half spin. And when the electron goes in, the other one points down, and that's what's referred to as having minus 1/2 in terms of the spin of the electron. So they have opposite spins. Electrons are affected by electrical fields. They have their own spin, so they go in opposite spins. And as we see here, this is a rule that tells us how two electrons can basically share an orbital. And what that means is Pauli's exclusion rule says that no two electrons can have the same 4 quantum numbers. And that's what's known as Pauli's exclusion rule, which essentially means we need to put one up and one down when we put it into an orbital. And when they have opposite spins, that is what is referred to as being paired. So the way I just drew these two electrons in this orbital, that would be referred to as having paired spins. And we'll see exactly why that is as we get into electron configuration as well, and why we have to kind of do it that way, and really what it means when we talk about having 4 different quantum numbers. Any questions on that so far? So let's take a look at so how we could figure out what orbitals are there on each energy level, and we could kind of build our energy levels here. So what I'm going to do, I think, is we'll skip that page there. So let's start with really the first energy level. And the first energy level is the n equals 1 level. So if n equals 1, what that means is L can have a value of 0 to n minus 1. So in this particular case, since n is equal to 1, I'm going to do the math without my calculator here, but I think 1 minus 1 is 0 in that case. So that means that the only value that we could have for L would be 0. Now, m sub L goes from minus L to 0 to plus L. And since in this particular case, the only L value that I got going on is 0, that means the only m sub L value I could have is also going to be 0 in this particular case. And what that means is for that particular guy, my m sub s can have a value of plus or minus 1/2. So I know you're thinking to yourself, that's a lot of numbers. What does it mean? And that's a good question. I'm thinking about what that means, but let's try it this way. Let's just kind of dissect what we got going on here. The n value is the energy level. All right. So n equals 1. So I'm going to draw my wonderful bad drawing down here and start way at the bottom. N equals 1. So I'm on my first energy level, lowest in energy. And what the L value tells me is really the type of orbital I got going on there. And in this particular case, if you have a 0 value, that represents an s orbital. So if you have a L value that has a value of 0, that represents the s orbital, which means it is telling me that on the first energy level, I have only the s orbital available to me. And how many of these guys do I have, basically? Are there 3D orientation? And I see only one number, which tells me there is only one type of s orbital present. And we commonly know that guy as, on the first energy level, the 1s orbital. And that's what these quantum numbers are telling us, that the only orbital on that very first energy level is just the 1s orbital. And the last quantum number here is telling me that I could put 2 electrons in that orbital, and each electron should go in a opposite direction if they are filled. By the way, first one goes up, second one goes down when it goes in there. And again, the one pointing up would be the plus 1/2 for the spin quantum number. The one pointing down would be the minus 1/2. And there is my first energy level. You may also recognize this when if you've written electron configuration before, which I hope you have since you're sitting in this class, but you always start with what orbital? You start with the 1s orbital. It is the lowest in energy, and that's because it's the only one there on the very first energy level. Now, if we move to the second energy level, and that would be the n equals 2 level. On the n equals 2 level, we have a L value that could go from 0 to n minus 1. So we can have an L value that is 0. We can also, on the second energy level, have a value that is 2 minus 1, which is 1. Now, what this tells me is we've already seen that the L value for 0 is the s orbital. You could probably guess maybe the L value that has a value of 1 is for our good friend, the p orbitals. So what this is already telling us based on quantum numbers is when we get to the second energy level, that is where we see s orbitals. And that is actually where we first start to see our p orbitals appear. Now, the thing that also confuses people is at this point, for every individual L value that we got going on, we could do an m sub L value. So I'm just going to kind of write it like this. So for my L value that's equal to 0, I could do an m sub L that would be 0, just like it was before. It would also have an m sub S of plus or minus 1/2. I could also do it for my guy with a 1. So if my L value is 1, my m sub L could go from minus L to 0 to plus L. So minus L would be minus 1, 0, and plus 1. If you count up all of those things, that is 1, 2, and 3 individual orbitals. And remember, this is our p subshell, right? And the p subshell has 1, 2, and 3 orbitals, right? And each of those could have an m sub s of plus or minus 1/2. Again, each of those can have a plus or minus 1/2. So if we're building our little table here, n is equal to 2. From our quantum numbers, we see that we have a 2s orbital. Again, the 2 means it's on the second energy level. Also could hang on to a couple of electrons. And we do see 1, 2, and 3 for our 2p orbitals to start to appear. And in terms of the m sub L, this again goes in order. This is minus 1, this is 0, and this is plus 1. This represents the px orbital, the py orbital, and the pz orbital. So pz is the plus 1 value, px is the minus 1 value, and py is the 0 value. You could get that specific in terms of knowing exactly where an electron is using quantum numbers. Any questions on that so far? So what I'm going to do now is to let you try this for n equals 3. Figure out all the acceptable quantum numbers for that energy level and what orbitals you got going on and everything. So see what you can come up with. Take a couple of minutes and then we will go through it here together. Okay, so let's take a look, see how we're doing. So again, we're going to start this off just like we did the other ones. It's going to come out kind of similar as well. So n equals 3. Again, L could have values of 0 to n minus 1. So obviously n minus 1 in this case is 2. So all of the acceptable values that we can find on the third energy level would be a value of L of 0, 1, and 2. As we've already seen, our 0 represents an s orbital. Our 1 represents the p subshells, right? And again, you probably could imagine that after SP, next comes our good friend D. The D subshell is represented by a L value of 2. So for each of these L values, as I've been mentioning, you can do your M sub L. So it is going to come out the same as what we saw previously. So for our L value of 0, our M sub L will be 0, just like it was before. And that will also, for that particular orbital, you could put an electron up or down in there, which would give it plus or minus 1/2 for its spin. Our L value of 1 will come out the same way as we just saw previously as well. Our M sub L can go from -1 to 0 to +1, again representing the px, py, and pz orbitals. And each of those individual orbitals can have a spin quantum number of plus or minus 1/2. So what this quantum number is telling us is when we get to the third energy level, we have s orbitals like we had everywhere. We have p orbitals still there. And this is where we first start to see the development of our d orbitals. So let's work out the one for our d orbital here, where our L would equal to 2. That means the M sub L can go from, remember, negative L to 0 to positive L. So what that means, negative L would be -2, -1, 0. Again, all whole numbers as you do this, going to our positive side of +1 and +2. Now, since this represents our d orbitals, and as you know, and as we talked about d orbitals, there is a grand total of 1, 2, 3, 4, and 5. That's what each of those numbers represent, the 5 different d orbitals that we normally just want d and a 5 next to it or something like that, or d and 10. And again, each one of those guys can put an electron either upwards or downwards. Again, upwards first, followed by down second in terms of their orbitals. So if we go back to our little energy level we're building here, again, based on our quantum numbers, we again see an s orbital present. We see p orbitals present as well. And now because we got to that L value of 2, we now first see our d orbitals appear, which obviously would be our 3d orbitals. Any questions on that so far? And lastly here, we'll just do one more here. If we went to the fourth energy level, possible L values on our fourth energy level would again be n minus 1, or 0 to n minus 1. So that's going to be 0, 1, 2, and 3. The 1 going to be our s orbital. The 0 being our s orbital, the 1 being our p orbitals, our subshell. The 2 being our, as we just saw, d. And if you remember electron configuration after d, that is going to be our f orbitals. Now for each one of these on here, just like we did on the previous slide, you could do your M sub L for 0, your M sub L for the 1, your M sub L for the 2. You will hit the same sort of numbers and stuff like that as we just did. So I'm not going to rewrite it. But again, if you did the first 3 quantum numbers, just like we did previously, you will end up with the same pattern right here as we did previously for those first 3. So let's just do the last L value. So the last L value here, which is 3, that means my M sub L value can go from negative L, which would be negative 3, to negative 2, to negative 1, to 0, to plus 1, plus 2, and plus 3. And again, this represents our F orbitals. And if you remember, your F orbitals contain 1, 2, 3, 4, 5, 6, and 7 different F orbitals. And each of those F orbitals can have an M sub S of plus or minus 1/2, depending on which way or which electron you are talking about. And in terms of the numbers, just like I wrote it right here, is exactly how they go. So we typically fill these orbitals left to right with electrons. And as we'll talk about, they go in one at a time and then come back and fill up. And you could get very specific as to, you know, which the quantum number is for that particular electron. So if we go to our last guy here that we will fill in on this chart, it obviously keeps going. We have obviously our 4s present on that energy level, our 4p present on that energy level, our 4d, and on that fourth energy level, that is where we start to see 1, 2, 3, 4, 5, 6, 7, our f's first start to appear. And you could kind of maybe see the electron configuration sort of order that you probably learned. And we'll talk more about that in just a second. But first off, any questions on how to assign quantum numbers here? Let me see what your question is there. They do. They do. The D's, for example, have x squared, y squared, and z squared, and y squared, and xy. They have some interesting sort of little letters next to it. I'm trying to think. I think we might even have a picture of it. I think. Let me see if we do. I think we do. I think we do. So to answer your question, why don't we jump ahead really quick to that there, I think. And we'll come back to this stuff here in just a second. Where are those pictures? Here's those pictures. So to answer your questions, let's take a look at those orbitals since we're talking about it. And this is in your notes just a little bit ahead. This is what the s orbitals look like. And as you can see, it really is just a sphere. It does get bigger as you go from one energy level to the next, but the circle just sort of theoretically gets bigger. Again, the nucleus sort of thought of in the middle, and that higher probability of finding an electron in there. And this again is what p orbitals look like. They're sort of like figure eights. And, you know, you could almost think of the nucleus sort of like, you know, right about there. So there's usually a pretty high probability of finding electrons sort of right around here on these guys. Again, as you sort of fan out, a little bit lower probability. So that's your px, py, and pz in terms of their orientation. And this is when we're talking about the m sub L number here. This is our -1, our 0, and our +1 that's happening here in terms of their orientation. And for our d orbitals, as you can see there, maybe your eyes are better than mine, but we have the squared ones and so forth. So they do have some letters on there. And again, you can kind of see here where it's darkest. You can kind of see this is sort of the center, almost like where the nucleus is thought of as being. And again, you can see this higher area of probability of finding an electron sort of in this area. And as you sort of go out this way, it's less and less dots, so lower probability as you sort of move away. And again, these are the d orbitals, and they do have little kind of subscripts underneath them as well. To be honest with you, for our purposes, you probably don't have to worry about the subscripts for those guys. Usually the X, Y, and Z for the P is the one that you see a lot, but they actually do have some. They really do look like kind of two p orbitals that have been put together, the Ds. Except for the last guy there, looks like a donut maybe with a p orbital going through the middle. And even our Fs, as you can see, also have some notation in terms of there. And for our class, you don't have to worry too much at all about those. You just need to know really that there's 7 in terms of the p orbitals. You don't have to necessarily give the notation of what they are. But again, you could kind of see they almost look like 2 Ds together, most of them. And then some look like that d orbital at the end that's been kind of split in 2 up there on top. But again, that's your 7 different f orbitals represented by those m sub l values of -2, -1, 0, +1, +2, and +3, maybe 1, 2, 3, 4, 5, 6, and -3 there. And we'll go with that, I think. And that's your 7 basically f orbitals that are present. Questions on that there? Okay, so let's go back and talk about a couple of kind of terminology that we commonly come across here. So a couple of words that we come across when we talk about sort of electrons, energy level, and those type of things. The first one really is what is referred to as a shell or level. And when we talk about a shell or level, which are 2 common ways to do that. So for example, if we're talking about the n equals 2 shell or level, we're talking about everybody that is contained on that level in terms of orbitals. So this would be like our n equals 2 level, or again, sometimes referred to as a shell. And you can see if we maxed out the number of electrons and filled up that entire shell with electrons, we would have 2 here, we would have 1 there, 1 there, 1 there. It would come back and pair off. And we would have 2, 4, 6, 8 electrons if we maxed it out, that n equals 2 level. Now, there's also something referred to as a subshell or sublevel. So for example, if I say, how many electrons could you put in a 3p subshell? This is a subshell or sublevel. It contains these 3 orbitals, which means if we max out our 3p subshell, we could put a maximum of 6 electrons in there. Now, if I said, how many electrons can we put in a 4d orbital? Take a second and think about how many electrons could you put in a 4d orbital? So the answer actually is 2. And that's usually the trick question that sometimes comes about. So remember that every individual orbital, no matter if it's a 3D orbital, 4D orbital, 4p orbital, 4f orbital, every individual orbital can only hold 2 electrons. So when I say how many electrons could you put in a 4D orbital, we could be talking about this orbital, which would be 2 electrons. We could be talking about the one next to it, which would be 2 electrons, or this one, or this one, or this one. So any individual orbital here could only hold 2 electrons. If I changed the question and asked you how many electrons if you filled up the 4D subshell, that answer would be 10 electrons, which might have been the answer you had previously. But that would be 10 electrons, because when we're talking about a subshell, we're talking about all those individual orbitals together. So those are sometimes how questions are asked. How many electrons in a shell or level, how many in a subshell, you know, how many in an orbital. Now, we sometimes don't want to like draw all this, right, to figure out perhaps how many electrons are on a level or a shell. So there is sort of a quick formula you could use to calculate that, and that is 2 times n squared. The n is the principal quantum number. So for example, the one that we did previously here, which is 2, n is equal to 2. 2 squared is 4. 4 times 2 is 8, which would be how many we could put in there. If we did the first energy level, n is equal to 1. 1 squared is 1. 1 times 2 is 2 electrons on that entire level. N equals 3. 3 squared is 9. 9 times 2 is 18. And that is how many, if we filled up the n equals 3 level, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 if we filled up that entire level. So that's a kind of a good little formula to remember. It will help you kind of quickly calculate it. Again, when you get into like n equals 5, n equals 6, and so forth, you may not want to obviously draw all that. Any questions on that there? So we did go to n equals 4, and we did get to f orbitals. So you may ask yourself, well, what happens if we go n equals 5, for example? N equals 5, all the possible values for L, why don't you figure out what all the possible values of L are? Just take a second, figure it out. So for L, the possible values should be 0 to n minus 1. So n minus 1 is 0, 1, 2, 3, and 4. So in terms of orbitals, right, you may be thinking to yourself, I think I took that class. I know this is an s orbital. I know we've been talking about that this is a p orbital. That's a d orbital. That's an f orbital. I didn't know there's more. So clearly there is more, right? Because I see some letters there and numbers. And how they go actually is alphabetical order after that. That was very creative. So after F, they just go alphabetical there. So what is that? That's A, B, C, D, E, F, G, perhaps? Yeah. And that's sort of how you would label L values past F, just alphabetical order for values of 4, and then 5 and 6 would just go in alphabetical order. We don't get into any of those orbitals in terms of electron configuration or anything like that. We still remain with just the Fs. But in theory, these theoretical orbitals and stuff that still exist technically just go alphabetical order after that. And obviously, you could do the same thing all the way through with that M sub L. It would be minus 4, minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3, and running on a screen plus 4 there. And you can see that if you did get to the theoretical G, you would have 1, 2, 3, 4, 5, 6, 7, 8, 9 different orbitals that would be present for that. Again, and everybody that's on the periodic table, we don't need to get past F, basically. But again, that is essentially what happens as you go past that. And again, you can't have n values that go up to 7. So again, you can get some of these different L ones. Any questions on so far quantum numbers, how to figure them out, or anything like that? You're professionals. I like it. That's good. That's good. All right. So the principal quantum number of n, we sort of, I think, got through some of these. So we'll just talk about the answer here. As we saw with an n equals 3 level, we can have L values that go from 0, 1, and 2, which means on our third energy level there, we do have s orbitals appear. We do have p orbitals. And again, that's where we first start to see our d orbitals appear. And again, those different types of orbitals are represented in quantum numbers by that L value that is there. And I think we probably got this guy as well. For L is equal to 2, again, you can go from minus L to 0 to positive L for M sub L of values. And again, that runs from -2 to -1 to 0, 1, and 2. And although it does tell you really the orientation of those orbitals in three-dimensional space, it also very simply tells you how many different orbitals you have by simply just counting these numbers. And again, that's 5 different orbitals, and that's what we expect for our d orbitals, which is what we're talking about in this case. And we talked about that. We talked about P. There's our Ds. There's our Fs. All right. So atoms with more than one sort of electron, there's sort of correlation problem in terms of the electrons and their pathways are really unknown. And obviously electrons which are negatively charged, when other electrons get near each other, you know, they're not super happy to be there because negative and negative really don't want to be near each other. They are able to sort of live with each other, but again, they don't really want to be very close to each other. So when electrons are placed in a particular quantum level, they prefer the order as we've seen S, P, D, and F in terms of how the electrons sort of go into the atom and where they're placed. And there is sort of an effect that occurs in terms of the energy levels of everybody. And it does affect the order at which electrons are put into an atom. And in the absence really of just actually, I shouldn't say that, in the presence of just one electron, for example, kind of like that little graph that we just made when we have the n equals 1, we have the 1s, or n equals 2, 2s, or 2p, or n equals 3. You know, we have our 3s, or 3p, and our 3d. And in the presence of really just like one electron, all of the orbitals are sort of equal in terms of energy. And what I mean by that is, as you can see in this maybe badly drawn thing on the bottom here, everybody in the second energy level, all those individual orbitals are pretty much equal in energy. Everybody on the third energy level, they're equal in energy. But what happens when we start to fill more electrons into the atom, when we get more than just one electron there? Because there's those electrons near electrons, there's actually a shift in terms of the energy levels of these guys and these orbitals. And that affects how electrons go into the atom. As you may know, and what we've been talking about, you know, electrons really do kind of go into the atom, kind of like how you walk stairs. You start on the bottom step and then go to the next step and then to the next step and then to the next step. And that's really how electrons sort of fill into the atom. They go in basically one at a time in the lowest energy orbital and then proceed to the next lowest and then to the next lowest. And when we start to put more than one electron, we actually will start to get some shifting in terms of these orbitals. So 1s will be here, 2s will be here, 2p will be a little bit higher in energy, and they're not everybody perfectly equal in terms of the energy of these orbitals. And that obviously will affect the order at which electrons will go into the atom. And when we do write electron configuration, and this is what this is sort of showing, sort of how far in distance from the atom it is. And again, you can see that there's some separation here between our S and our P in terms of how far they are from the actual nucleus. And here as well for our 3s orbital in terms of how far it could get. And really what this affects is the order, or the natural sort of order that you would imagine electrons go in. And the way electrons actually do go into the atom is through this order here. And this is something that you could kind of create pretty easily by yourself. You go 1s, 2s, 3s, 4s, 5s, 6s, and 7s. And if you remember, n goes from 1 through 7, so that's what that is. On the first energy level, if you remember from our quantum numbers talk, we have the s orbitals. It's not until we get to the second energy level, right, that we see the p's occur, and go 3p, 4p, 5p, 6p, 7p. And if you remember, on the second energy level, there's an S and a P. And it's not until the third energy level that we have an S, a P, and a D start to occur. So 3D, 4D, 5D, 6D. And it's not to that fourth energy level like we did, based on our quantum numbers, that we start to see our Fs occur. And this is the order at which electrons really go into the atom. It is sometimes referred to as the filling order. And how it works is you basically will always, when you go to write electron configuration, always start up here. And you basically go this way. And then when you're done to the arrow, you zigzag back this way. And you keep kind of zigzagging back and forth here. And this will give you the proper filling order for an atom. Again, zigzag back and keep going. And where you really start to see the difference is if we follow this zigzag, the electrons first go into the 1s orbitals, then they come back and go into the 2s orbitals, then they come back and go into the 2p orbitals, then the 3s orbitals, then they come back and go into the 3p orbitals. And this is really where that change in energy really occurs. After the 3p orbitals, the next lowest in energy is actually the 4s orbital. So they get the electrons first, then it zigzags back to the 3d, 4p, 5s, 4d again. So you got that same 5s back to 4d, 5p, 6s, and keep zigzagging back and forth. And you do need to know this. And the nice thing about that is, as you just saw me do it, it is something that you can recreate pretty easily on a piece of paper. If you know this, which you've probably seen some version of this, I'm assuming, in chemistry, and you know the idea of what we talked about, that an s orbital could hold a maximum number of 2 electrons. If you could fill up all the p orbitals, they could hold a maximum of 6 electrons. D orbitals, the maximum of 10 electrons, and our f orbitals, a maximum of 14 electrons. You pretty much can write any electron configuration that you would need to do. So again, that's sort of an important thing, getting the proper order for writing electron configurations. And again, if you pretty much know those two basic things, or how to create those two basic things, you definitely should be able to write any of those electron configurations that you need. So let us start writing some electron configurations, and we're going to tie this into our quantum numbers so you can see how that sort of works together, how the electrons work, and all that good stuff. So no better place to start than with good old number 1 on the periodic table. Number 1 on the periodic table, I'll refer to it. It looks like hydrogen still. That's good. So hydrogen's atomic number is 1, which means if it has 1 proton, which is its atomic number, if it is neutral, it should also have 1 electron. So again, we would start at the top here, and we would go 1s1 would be the electron configuration for hydrogen. The first number here is the principal quantum number, that n number. The S here is obviously the orbital that our electrons in, and the number on top is how many electrons are in that orbital. And that is how you say it, 1s1. That is also how you write it. It is a 1, a lowercase s, and a superscript up on top, I think, 1 up on top. So 1s1. So this is the electron configuration for hydrogen. We can also represent electron configuration by what is referred to as an orbital diagram. And an orbital diagram is either boxes or lines to represent the orbitals. So I'm just going to use a line. Again, sometimes people will use boxes. And this would be our 1s orbital. And for hydrogen, when that first electron goes in, it goes in the upwards direction. Any questions on that so far? So let us now tie this to our, maybe grab something here. Let us tie this to our quantum numbers. I'm going to ask you to try it first. Can you give me the 4 quantum numbers for that electron? So why don't you give it a try and see what you come up with. I want the 4 quantum numbers that represents that particular electron right there. Okay, so let's see what you came up with. So if you're not sure where to start, you could actually start with the electron configuration. So as we said up here, this first one represents the principal quantum number, right? And the principal quantum number is the n number. So right off the bat, we know that n should equal 1. Now, if n equals 1, like we were talking about, L could have a value of 0, which is good because this represents the s orbital, which is good. And the m sub L in this case, because this one is 0, would be 0 as well. So that's still good. There's only one s orbital present. And the m sub s in this case would be plus a half. Not plus and minus a half. It is actually just plus a half because this electron is the first one in the orbital and it has what is designated as positive a half spin. These would represent the 4 quantum numbers for the very first electron here, and the only electron in hydrogen would be represented by those 4 quantum numbers. Any questions on that? So why don't you write the electron configuration for helium, which is number 2. Why don't you also draw the orbital diagram for helium? And finally, why don't you write the 4 quantum numbers for the second electron in hydrogen or helium? So take a moment and do that. Okay, so since we're getting to the end here, let's take a look. So again, in terms of electron configuration, again, going to start at the top, and we're going to go 1s2 in terms of its electron configuration. That means, again, when we go to the orbital diagram, we do have an electron that goes up. And now we have that second electron. And again, we have really 2 options as to how we can put it in. We could decide to put it in the same way. We could, I guess, go opposite ways. And the reason that, as you probably know, and as I talked about earlier, we go with this approach is because if we went with this approach here, where we put them both in the same direction, the quantum numbers for this electron on the left would end up exactly like what we just did. And if you did it for the guy on the right, it would end up exactly like we did there as well. And on that slide that we saw earlier, which is the Pauli exclusion rule, the Pauli exclusion rule says that no two electrons that are sharing the same orbital can have the same four quantum numbers, which is in this case, they would have the same four quantum numbers. Even if you flip them both down, they would both have the same quantum numbers. So that is why we do not put them in the same direction. Now, when we put them in opposite directions, again, that first one ends up with the exact same quantum numbers here. But now if we look for the quantum number for this particular electron, n is going to equal 1, L will equal 0, M sub L will also equal 0. And you may be saying to yourself, this is looking very much like this deal here. The difference, though, is with my electron heading in the downward direction, my spin quantum number is minus a half, not plus a half. And that little difference about how the electrons go into that orbital makes it not violate Pauli's exclusion rule, because they technically now do not have the same four exact quantum numbers. And that is the long story for put an arrow up and put an arrow down in the same orbital when two electrons share the orbitals. Question on that there. You could also see, you could get extremely specific in terms of quantum numbers and do it for every individual electron and figure out what it is. Any questions on that so far there? Okay, so I think what we're going to do today is we're going to stop for now. Yes. And I've decided that I'm going to reward you by, continuing lecturing to you. So we're going to do some more electron configuration, a little bit more of these quantum numbers in lab today, and then we're going to call it a day, I think. And we're going to move the experiment from today till Tuesday. So we'll do experiment number 3, I think it is, on Tuesday. Just to kind of keep us on track, we're just going to do a little bit more lecturing, get through sort of electron configuration and so a little bit more about these quantum numbers. That should set us up nicely for Tuesday to get into some of the periodic trends and finish this chapter. And then that will help you with experiment 3, which deals with some periodic trends. So we're just going to lecture for a little bit at the opening of the lab on the stuff right here through some electron configuration, quantum numbers. And then when everybody falls asleep, including myself, we'll call it a night, and we'll move the experiment to Tuesday. Any questions on that? Okay. Yeah.
So the only thing that's due by the end of tonight is the experiment from last class, right?
That's correct. So experiment 2, if you haven't uploaded it yet, is due by the end of the class period. Yep.
Okay.
Any other questions? Okay, so if you didn't put it here in the chat box, make sure you do that. I'll see everybody about 7:15-ish. And again, we'll just continue lecturing on this and doing some more electron configurations and examples.